Hello, we're gonna wait for a couple of minutes to start so everyone can join, and we'll start in probably in a couple of minutes, 2 or 3 minutes. Okay, so let's start. It's time. We give time people to join. First of all, we're gonna do questions at the end. There is in the panel. You probably can see a question mark. You can go there and ask anytime any question, and at the end we'll try to answer them all. Jank is here with me, and she will be helping on that end as well. So let's start. We're on that. Welcome everyone to today's webinar. We're going to be talking about storage optimization for containers on AWS. So to start and to give a bit of context, who am I? My name is Ferran. I'm an engineer at the company, and I've been at the company for 4 years. I have a background on infrastructure engineering. Now let's pass to a bit more interesting things, actually, on that and what Ondat does. So before we go straight into Amazon Web Services, storage, let me give you a bit of an architectural understanding of what we do. So Ondat is a software-defined storage platform implemented for containers, or more precisely, for productionized workloads that require statefulness. And to build on that, we did so with specific principles in mind. And those principles had to fulfill core beliefs into the cloud native storage principles. Any storage system that is designed for containers have or should have, at least in our opinion, a few important points. One, being declarative and self-service, being an application-centric. It needs to be secure, no doubt. We cipher on the wire, and we have encryption on encryption at rest to keep all data safe at any point in time. We implement high availability with automatic failover, so synchronous replication, etc. So we have built this on that functionality based on these core principles. And how do we install? So we install in almost any distro of Linux that can run Kubernetes. It's agnostic and can run in almost any Kubernetes distribution or flavor, if you want to call it that way, whether it's OpenShift, Rancher, managed services like EKS or GKE. Now, we install with an operator. So Ondat installs with an operator first, and then we deploy different components. The main one being the Ondat node that you can see at the top row of this diagram. And that is what the key of the product, in my opinion, because it transforms your worker nodes, where the worker nodes that you run Kubernetes on, into an array of storage with all the cloud native principles behind. So what we are doing is aggregating the capacity of those nodes, the physical capacity of disk of those nodes, and virtualize them. And then we can provision Ondat volumes, you can think of the Ondat volumes as persistent volume claims, or a one-to-one mapping to a persistent volume claim in Kubernetes. And we will use that commodity hardware to provision and to serve the data. On top of that, we have different components to give smooth integration with Kubernetes. So today, we're going to talk about storage. We're going to talk mainly about AWS and its architectural models centered on optimization. But before that, I wanted to present to you, or to expose some pattern that we as a company and our customers keep seeing. And it's a model where we can run on that in every node of the cluster and use the disk on every single EC2 instance of the cluster to store data and to present data. But more and more, we see this model where people deploy different different node pools for stateful applications and for stateless applications. It's very traditional and very common to keep a centralized deployment, and it's something that we support on demand. So you keep data in a few nodes, and we access data through the network, right? That's a very centralized style. And many storage systems do that. But at Ondat, we want more flexibility, so we can run in hyperconverged. So you can deploy your pod, your application that requires data anywhere in the cluster, and at the same time, you can centralize if you want, and keep data in one place. But we are seeing more and more this model where we have a hybrid architecture in terms of those clusters deployed in a very flexible environments, such as Amazon Web Services. So what we see is a node pool with stateful applications. Think about Elasticsearch, MySQL, Postgres, Kafkas. And not only the data is on those nodes, but those applications as well. And then we keep more stateless style applications, batch jobs, web servers, and you could think of as deployments in Kubernetes in a different node group. And you can call it node group, node pool, instance group. It depends what you use to provision the cluster. You would call it in one way or another. But in the end, what we want is different scaling policies. Why? Because when we keep data stored in the nodes, that life cycle of those applications and the stability of those applications is not the same as stateless applications. And for that reason, we can keep web applications scaling very aggressively in terms of nodes and pods. And we can keep stateful applications on nodes that have more conservative scaling policies, mainly scaling down, because we want to keep data. So I wanted to discuss this with you because I find quite interesting that this is more and more common nowadays without scaling groups. Let's go deep into the performance side of things, the optimization of cost, performance, and what we get for what we pay. We extensively test on that and different solutions, and we do highly complex benchmarks in the company. But today I want to show you something which is more of a summary of those benchmarks and more of a conclusions of what we see. And for that, we prepared two scenarios. The first one is comparing using Ondat while using a backend EC2 instance that uses GP3 volumes, so EBS volumes, versus provisioning a PVC straight to GP3 storage class. This is the first scenario. And what we're doing here is deploying a PVC on EBS on GP3, and then comparing it to a volume that is replicated, and on that volume, replicated, so we write synchronously to two different nodes. The node where the application, for instance, is running, the benchmarking tool is running, and then another node. And every time we do a write, that write goes to both nodes. It gets written into a backend disk, in this case, also GP3. And then when that write is done, we acknowledge that the file system, and therefore the write is finalized. So what we can see here is that for writes, there is no caching and things like that for writes, we almost get the same result. Why? Because I'm using a default GP3 volume or EBS disk, and that has a default of 3,000 IOPS, input-output operations per second. What we can see that it's quite outstanding here is the IOPS on the reads for the Ondat volume. What is happening here? Well, Ondat is capable to stack up a lot of the I/O and do a lot of write-through caching. So for reads, we maximize the use of the EBS. So not only we are comparing GP3, we're also using Ondat, maximizing that performance. Mainly on reads. There is no magic on writes. I mean, writes need to go to disk. However, one interesting point here is that on the writes from that, even though we're writing to two different nodes backed up by EBS, we see a similar performance on the client side. And you could say, how is it possible if we're going to the network? Well, the difference factor in between going to the EBS backstore is so much bigger than replicating in between two EC2 instances that we can barely see a difference. And obviously, there is a margin of error and a percentage of benchmarking errors. So on the next metric, we're going to do IOPS bandwidth and latency, which are probably the most common attributes to look for in benchmarks. We can see a similar result. We see writes that cap at 125 megabytes per second, which is the default of a GP3 volume. I didn't add provision IOPS or provision bandwidth, so just standard default. And we can see that once again, through this layer of caching and this layer of smart optimization of reads and block sizes and the way we write to disk, or actually we read to disk, we can maximize the bandwidth. There is a factor to take into consideration here, which is going to the network versus not going to the network. And we can see the difference here is quite significant. It's true that on very thorough benchmark, you could see here define which block size we use, what queue depth, etc., etc. But here is probably an oversimplification, but an example nonetheless to give you a bit of an idea of what we're seeing here. And this is the result of having multiple benchmarks with multiple block sizes, all using the direct flags to avoid a lot of buffering, mainly on writes. So finally, what we can see, and here is where we can see a very important metric, which is the latency. In my opinion, one of the most important metrics when it comes to databases. So what we need is the lowest latency possible for anything that requires high throughput. And here we can see how going to the network, no surprises there, but going to the network takes way longer than leveraging on that to read data from the local disk, even though it's an EBS. We can maximize that throughput and also that latency. Keep in mind that we did a test with a 50 gigabyte file on with FIO, and that means that it's not fitting all in memory, because it's an important thing to take into consideration. So we can see that using Ondat versus GP3 volumes for a unit, so for one volume only, we can see a benefit of using Ondat with GP3, and we are maximizing GP3. So for the amount of money, for instance, that we pay for that volume, we're getting a bit more, mainly on the reads side of things. I have to say that the GP3 is quite a good technology, and you can see that here. This is the second scenario. The second scenario is a bit different. We're going to use Ondat persistent volume claims, so Ondat volumes on Kubernetes, all with one replica, meaning two copies of data. So every time we do a write, we write into one node on another node, and when both acknowledge the write, that write is finished and acknowledged. And we're going to compare using Ondat on EC2 instances that have a backend disk of GP2, an EBS type of GP2, using in blue the NVMe, or what Amazon refers as ephemeral disks. Some type of instances on EC2 can allow you to mount the NVMEs of the physical host, and on GP3. So now all the volumes are replicated, and we will see the difference between reading and writing to different backend storages. So it's no secret here. It's nothing that you cannot guess. Is that when you write locally to the NVMe is miles faster. So here we can see over 70,000 IOPS, even though we are replicating. Obviously, for reads, you don't need to go to the network because it's local. But for writes, we need to write to different places, go to the network, and that drops. to around 20,000 IOPS. Still, the difference between the 20,000 IOPS in grids and, let's say, with GP3 on the far right side of the diagram is that you hit the IOPS capped on the EBS around a bit lower than 3,000, more or less 3,000. What's interesting here is that GP2 volumes are burstable. And here in this test, they are all fresh, so they are not bursted. But they are more unpredictable and less, in the end, less predictable. They change on their performance quite often. So in this case, a GP3, it's a much more stable and much better technology for using EBS. Once again, if we check the bandwidth, no surprises here. The bandwidth is much faster on local NVMEs. And in the end, we can see that the bandwidth, mainly for grids, caps out of the 125 megabytes that GP3 has. However, you can see that GP2 on orange here has a more unpredictable performance, and that is because their performance depends on IOPS per gigabyte. So the bigger the volume, the bigger the EBS, the more performance we get out of it. Instead, GP3 doesn't have that limitation, and it guarantees a 3,000 IOPS. And I believe it says 10% of the time. But in general, it works pretty well. No surprise that we can get the maximum bandwidth on NVMEs local to disk. But there is one thing to take into consideration. The local NVMEs also are capped, and depends on the instances, you have more or less. And that is because it's a hypervisor host, or we use a hypervisor in the host, and every VM has some chunk of the resources for those disks. Even though they are local, they are not full on just for your VM, which actually is fairly reasonable. And if we check the latency, what we can see here is the biggest differentiator, which is how fast or how long it takes to do actually one read or one write. We're looking at 65 microseconds to do a read, local NVMe, local disk, no network, we're fast, comparing to accessing the EBS backstore, whether it's GP2 or GP3. The difference is massive. And still, we can see, once again, that GP3 is a fairly much better option than GP2 when it comes to performance, at least. Now, all this is no surprise, but we run the numbers, we see the data. But what we don't have with the NVMEs, and what is the big concern, is that the NVMEs are called ephemeral for a reason. And they're called ephemeral because every time you terminate an EC2 instance, that data is gone. Whether with EBS, you can plug it once again on a different node. Now, availability is fundamental. But keep in mind that every single test that we've done is enabling the Ondat replication. And that means 2 copies of data, you can increase that to 3, 4, 5. So obviously there is a performance impact the more replicas you add, because we need to write to more places, even though it's in parallel. But you can increase to 2 replicas, meaning 3 copies of data, and therefore even achieving the availability that you need per volume. So you might want 99.98% of availability, like for instance IO2 on EBS gives you, or you can guarantee more by having more replicas. Now, what is the next step here? NVMe is way faster. No surprises there. We have availability thanks to Ondat. But what is the big difference? The big difference comes into the cost. How much are we getting for how much are we paying? Now, if we look at cost optimization, we're going to talk about a real use case that we studied, but let me discuss a few different profiles of I/O. There are many profiles of input-output operations, but I'm going to cover 2 very common ones, and maybe a bit naively, but we need to understand what we're paying for, to understand where are we missing and where are we not getting the most out of our resources. So in this case, I want to discuss the I/O pattern of constant cyclical pulse of grids. Think about monitoring. Constant grids, maybe not that big in amount, but fairly constant, and it cannot slow down. It's always similar pace. It's true that in some technologies, for instance, for monitoring, it will keep growing eventually, or you can have some peaks, but over time is a fairly flat line. You can think of stream of messages with Kafka that are fairly stable, or log ingestions with Elasticsearch or Loki, for instance. Very common patterns that we see every day. We need to take into consideration that if we use an EBS volume as a PVC every time we need one of those applications, easily you can run around 20 to 30 EBS volumes as PVCs for maintenance and for a common application. And if you have a larger cluster, you can easily end up with 100, 150 PVCs without a problem. And every time you have one of these PVCs, for instance, with Prometheus, that is not highly utilized, you are losing money. You are paying for 3,000 IOPS that you are not using. And then it comes to different IO pattern. A more traditional style IO pattern using, for instance, relational databases, searches, or a stream of messages that come in and come out. For instance, let's say trading at 9 a.m. in the morning, there is going to be a spike of trades, while at 9 p.m. maybe it's a flat line almost to zero, or there is no messages coming. So we can see spikes of traffic. Still, it's more difficult to prevent, and we are paying, as always, for the maximum peak that we need to be able to give service. But what about all that area that we are not utilizing? And this is a very similar approach that Amazon fulfill with virtual machines. I have hosts, they are underutilized most of the time. I'm going to share resources such as CPU and memory. And then with that, I'm going to be able to manage the traffic and making the problem smaller. So using Ondat, we can achieve the same to maximize resource utilization and therefore minimizing cost. So we can stack the I/O. We have backend disks, let's say 1 or 2 EBSs for each EC2 instance, or even the local NVMEs, and we can leverage on that to stack those IOPS. The performance I show you, the benchmarks, are for one unit, one PVC only. But what when you have hundreds of PVCs? If you have hundreds of EBSs, you have a big overhead of things, of underutilized resources. While if you use Ondat, because we virtualize those disks, the input-output operations end up going to the same physical disk. It's designed for multi-tenancy, so the data from a binary point of view cannot be seen from one PVC to another at any point in time. It's just by design impossible. They have different binary paths, but the medium where it's written is the same. So we can maximize, let's say we have 3,000 IOPS because we are provisioning that EBS. We can have multiple PVCs to utilize maximum and at all times. On top of that, we are guaranteeing that utilization through synchronous copies of data. So we have high availability and automatic failover. If you keep thinking about EBSs and we're talking about prices, there is another thing to take into consideration, which is the container-centric storage. EBSs are designed for virtual machines. That means that they're provisioning and there are operational factors that need to be taken into consideration. I'm gonna go there when we talk about operations. But before that, I want to talk about the use case. A real use case. We did a study, and I oversimplified this massively to keep it simple. We did a study with a customer. It's a large enterprise that works in media, and they have hundreds of databases in RDS. They have Kubernetes clusters. We're talking about maybe 40, 50 RDS instances. And they have an expenditure. We simplify that to keep unit into RDS, 1AZ, so no multi-AZ, and provision IOPS. Obviously, for high availability and production, they use RDS with multi-AZ. But in any case, to simplify the problem, we end up getting into the price tag of 1.5 million a year on RDS with provision IOPS to serve all the databases that their company requires. Now, we did the study, And we put similar resources in terms of CPU, memory, capacity, etc. And it came down to less than 10% using local NVMEs and 2 replicas, meaning 3 copies of data of every single input-output operation is synchronized to 3 different nodes. Now, that comes to a less than a 10% of cost. We're talking about $100,000 a year. Obviously, you need to factor the operations that RDS gives you, such as automatic backups and things like that. But that's your decision to make. Do I want to implement that in a fairly simple way as a database as a service, for instance, and leveraging Kubernetes, or keep using RDS and having a price tag that is most often underutilized in many cases, and having a big price tag? So we did this use case. It's a real use case, and I wanted to show you how much is the difference. Keep in mind what we saw before in terms of performance, IOPS and bandwidth and latency, in between using EBS volumes and local NVMe. And here is where the difference in price is the highest. Using the local NVMEs reduces the price per IOP dramatically. And here is where we can see that difference. Finally, I'm going to talk a bit of operations, and from the perspective of cost, both of human cost and financial cost when it comes to certain operations. Now, we're discussing before about container-centric storage instead of storage designed for virtual machines. When you deploy EBS, you have some limitations when it comes to containers, and those principles that we defined initially from the cloud native storage core principles. You need to be able to provision hundreds of volumes in the same way that you provision hundreds of pods. And that should not have too much of an overhead. With Ondat, we can do that and let EBS to be used for virtual machines. We're going to use EBS in the end, or local NVMEs, but GP3 nodes as well. They're pretty good. But we're not going to take seconds or minutes that sometimes EBS take to provision, to delete. If we have a failure on a node that EBS need to be reattached on a different node, that can take failovers that are blocked or take minutes to recover. We want something a bit more flexible and faster, designed for containers, because containers move really fast on different nodes. So let's leave EBS for what it's really good at. Let's leverage that, and let's tag up I/O using Ondat. All of these on top of being able to define how many replicas you need per volume. So that means that operationally, you can define the priority class and storage, and you can define that in storage class of how important that data is and how much availability do you need to guarantee if you have SLAs and things like that. On top of that, we can do a topology-aware replacement. What does that mean? It means that we can send the replicas across different failure domains. In Amazon, for instance, this can be different availability zones. There is cost in the traffic across AZ. Yeah, you need to take that into consideration. But keep in mind that EBSs cannot do that. They can export snapshots in between AZs and regions, but you cannot do synchronous replication. And that means that if you have failure on one availability zone, you can guarantee that there is data on a different AZ, different failure domain. So once again, we can let EBS to work where it's really good at, and have even more guarantees if we use, for instance, local NVMe's disk to have more availability. And finally, we can horizontally scale. We can just add more nodes, and because Ondat installs Ondat operator installs daemon set, the main controller, we can just add more nodes. We add more nodes, we have more capacity. We can even plug more EBS disks into the nodes, give that to Ondat, and we parallelize and we have more availability. Now, this is the good things that we can get out of it. But what about the more difficult things, or the things that we need to take into consideration or be careful with? GP3, we compared GP3 and GP2 before, and I think for containers, GP3 is a much better option. GP2 being burstable is very problematic for containers, and even though you have provision IOPS, you have IOPS per gigabyte in terms of performance. That for containers can be very problematic, because in the end, what you're having is smaller volumes, let's say 50 gigs, 100 gigs, 15 gigs, and many more, rather than having 1 TB of an EBS for one database. It's more common to have small volumes. And that means that having a GP3 volume is much more effective. However, GP3 requires installing a CSI driver. You can do that with Helm, but also you have to configure IAMs, meaning there is an operational burden to do that. I believe that Amazon announced fairly recently that in EKS, they're adding the add-on that you will be able to click or put into an EKS CTL some configuration to add GP3 as a storage class, but still not there yet. And that means that it takes some burden and some time to deploy that CSI driver. Now, one big caveat when it comes to using the NVMe local drives is that those drives are static in size per VM. You cannot expand those disks. However, when you use EBS, you can expand EBS, or you can even tell Ondat, here is another EBS, plug multiple in one node, and we will stripe the data across different EBS devices. You have to be careful because there is a maximum EBS attachment per virtual machine, and that the main reason is the overhead that mounting EBSs into VMs have in terms of network and CPU. So it depends on the instance size. We are talking between 16 and 25 EBSs per node, and still the machines need to be gigantic to be able to handle that. While if you have 1 to 4 EBSs in one node as a backend on that, you can have hundreds of volumes because we virtualize that. And the hundreds of volumes that you can have, in the end, they will grad to these 4 or 5 EBSs that you might have per machine, and still not have the overhead because it's almost for free that you have on that volumes. And finally, you need to take into consideration that if you do that, you would need node selectors and tains according to the kind of workload, because you will need to be a bit more detailed on where you store data. That's about it. So in conclusion, if you want to save in cost, you can leverage on that to run an ephemeral disk. If you're willing to get a bit more availability, even though the volumes are replicated, but you don't want to have to take too much care about scaling policies and things like that, you can use GP3 volumes, and it will be more pricey. You pay in the end for having the peace of mind that things are more maintained for you. So to finish here, and I'm going to go to the questions soon. As a call of actions, we finish what I wanted to present today. You can go to the website, and we have a white paper for AWS and Kubernetes, and it's quite detailed information. I think it's very interesting. And you can go and play. We have playground scenarios where you can use on that without even having to install in your cluster. It's like a sandbox in a web browser. It's actually really cool and really fun. You can sign into the portal, which is a SaaS offering that we released quite recently, and you can sign up there, generate free licenses, install your cluster, and get quite a lot of interesting functionality. Finally, I wanted to mention that we're going to be in the AWS Summit next week in London. The company is based in London, so if you happen to be around or you want to go, come visit us. We're going to be there, and we're really happy to meet, just to learn for your use cases, whether you use on that or not. We are always really interested in the ecosystem. And I wanted to mention before I finish that we are also hiring. We're expanding our team, and if anyone wants to join or has anyone that is interested in technology, we're open for new candidates. So now we're gonna pass to questions, and I'm gonna stop for a second. So you're gonna stop listening for a few seconds and probably be happy about it.
Hi guys. So we have a few questions. Ferran, for you. Why does the GP3 storage class need a CSI provisioner added, but the GP2 doesn't?
Mm-hmm. So this is a historical reason. All modern drivers need a CSI provisioner. On that, when installs, for instance, the operator automatically installs that for you, and it's the glue in between the Kubernetes API and the storage provider. The GP2 it's a storage class that comes, it's a bit older. And before the CSI existed, GP2, the GP2 provisioner, and for instance, on that, at that time, we're talking about maybe 3 or 4 years ago, was in the source code of Kubernetes itself as a storage provider. So the storage class, if you look at the GP2, is baked into the Kubernetes source code. This is being decommissioned, and really soon, and over different versions of Kubernetes, this is being removed. And on that, for instance, we removed all the code that we had in the trunk of Kubernetes to implement a full CSI solution, which is implementing the primitives that are given through an API exposed. So GP3, being a newer technology, is only supporting the new way of doing things.
Great, thanks. Someone else has just asked, does Ondat have read-write many support? How does it compare to EFS?
So today on the benchmark, I didn't show comparing to EFS, but it could be probably a different talk. Yes, I've been talking about block storage today and centering on applications such as databases. But yes, Ondat implements a read-write-many solution on top of the high available solution that we already have, and it's a shared file technology that allows you to mount the same file system on different pods. For instance, think about web servers or shared file systems like NFS. So how does that compare to EFS? Well, first, EFS is, we would need to show a lot of diagrams and proper benchmarking, but EFS has a performance, it's a bit unpredictable in terms of performance because it depends on the size that the EBS is used, even though you're not really defining the size. So the more you use the EFS, the faster it gets. It uses a backend on S3 objects. So it's EFS is very flexible, but it's not built for performance. So when it comes to performance, the Ondat solution is a bit faster, mainly because the data is a bit closer and it doesn't have to go as far through the network to get that data on read-write-many volumes. So that could bring, or that could lead us to different conversation. But yeah, we do have read-write-many support, and the provisioning, I have to say, it's actually completely trivial. If you ever had to provision an EFS, you need to provision a PB or use a dynamic provisioning, different CSI driver. It has a bit of an operational burden. The Ondat read-write-many is provisioned as the same as you do with read-write-one volume. It's just in storage class, or even your PVC, you can define that. So it's fairly simple and trivial to do.
Cool. Okay. And there's one more that's come in. Do the applications need to run on the same node as its data?
So maybe that's not initially obvious if you're not familiar with Ondat. Ondat can present data on any node in the cluster. That means that you can run your applications wherever worker that your application runs. It doesn't matter if it's in the same node. And actually, we tell Kubernetes, we influence Kubernetes a little bit, saying, hey, data is there. Try to put the application close by because you're going to get the fastest latency or the smallest latency, so the best performance. But it doesn't have to be that way. You can deploy the pod anywhere in the cluster, and as soon as Ondat is installed, we will handle all the network connectivity for you, and automatically we will create the network paths, and the data will flow to where the primary volumes are located, or is located actually. So no, it does not have to be. This is something that in a storage class like EBS, you need to wait for the first consumer. If you look at the storage class details, and that means that the EBS and the pod need to be running on the same node. So if the pod needs to move somewhere else, the EBS needs to follow. That can take time. This is not the case. We can just mount through the network in milliseconds.
Cool. Okay, and how another one's just come through. Does Ondat run in production?
So Ondat is a company that got renamed fairly recently. Before it was called StorageOS, and this is a 5-year-old company. So yes, we run in production. We have been running in production actually for more than 3-4 years easily. And even though we keep evolving the technology really fast and really often, we have many production customers that run, for instance, banks or media companies I mentioned before, that run their production workloads, their stateful databases on top of on that. And also we find, for instance, service providers like data centers that implement their solutions to their end customers through Ondat as their storage system for containers as well. So yeah, definitely.
Okay, I'm just conscious of time, so we'll take one more, and then if there are any more questions, we can answer them offline. What tools did you use to generate the benchmarks?
So in the company, we use different tools, and mainly we use FIO for synthetics benchmarking, and what I presented today is based on FIO. We use also dbench, which is a set of using FIO. FIO is an open source tool, and on top of that, we also do application benchmarking that we do specific for each application. So we would use, for instance, the injecting load with the Kafka tools, or with Postgres, its own tool with pgbench, and we use different tools for that. Today I presented with FIO, but FIO is a binary, is a very extended tool used in the industry, and we have a few containers that we have the FIO there. So this is actually open source. What we use and what I actually use today, it's something you can run. You can run to the Ondat GitHub page, and you can find there in the use cases, you can find the FIO benchmarking already cooked, already prepared. So you can just go deploy, and it will give you the numbers of your cluster or your infrastructure, and run the same benchmark that I actually did run today.
Amazing. Well, thank you so much, Ferran, for your time. And this concludes the webinar.
Thank you, Janky, and thank you everyone for coming today.
Thanks. Take care. Bye.